In this video, I'm going to show you how the central limit theorem works. So in other words, I'm going to show you the central limit theorem in action. Okay, so for example here, this graph represents the parent population. You can see that the shape of this graph is bell-shaped and symmetric, so you can say that this graph, which is the population, is normally distributed. And over here on the left, you can see that the mean is equal to 16, and the standard deviation of our population is equal to 5. Okay, so what we're going to do is we're going to simulate the central limit theorem. Okay, so for example, for a sample size of n equal to 5, okay, what's going to happen is, when I click the animated button, it's going to randomly select 5 values from the parent population. Okay, and then in this graph, it's going to calculate the mean of that sample. Okay, so these are the 5 randomly selected values from the population, and then the resulting sample mean is represented by this blue box here. Let's click on it again. Okay, so we get 5 more randomly selected values from the population, and then the sample mean ended up here. Let's do it again. So once again, these are 5 randomly selected values, and the sample mean landed here. Here we do it again, and the sample mean is here. Okay, so notice that for each sample of size 5, okay, this is our sample size, right, we get a different sample mean. Okay, and the sample means are being graphed in this grid below. All right, we're going to repeatedly do this, right, for different samples of size 5, okay, to see what the distribution of the sample mean is. All right, and you can't really tell anything at this point, right? There isn't a definite shape that the sample means are making when we graph them. Okay, so we've done this 10 times, so we've randomly selected 10 different samples, each with a sample size of 5. Okay, and the graph of the sample means looks as follows. Okay, so according to the central limit theorem, if the population is normally distributed, which it is, right, then the distribution of the sample means is also normally distributed. Okay, so what we're going to do is we're going to simulate more samples. Okay, so 5 more samples, 5 more, and so on. So as we're doing this, as we're taking more and more samples from our population, right, this is the graph of the sample means. So the number of reps tells you how many samples you've selected so far. Okay, the mean of the sample means so far is 9.66, and then the standard deviation is equal to 8.12. Okay, so we're going to keep doing this, taking more and more random samples from this population, and calculating the sample mean for each one, and then graphing the resulting sample means below. And as we take more and more sample means from our population, right, you can see that the sample mean changes, and so does the sample standard deviation. The sample mean, the means of the sample means, okay, and the standard deviation of the sample means also changes. Okay. So we're not going to notice the effect until we collect more and more samples. So let's do 10,000 samples and see what happens. And as you can see, right, when we add 10,000 more samples from this population, right, we can see that the graph of the sample means is bell-shaped and symmetric. Okay, so the sample means are definitely normally distributed. Okay, the mean of the sample means should be equal to the population mean, which it is. So the mean of the population is 16. The mean of the sample means is also equal to 16. Okay, but what about the standard deviation? Right here, the standard deviation of the sample means is equal to 2.28. Okay, and the standard deviation of the population is equal to 5. Alright, so as we collect more and more samples and then look at the sample means, right, we see that the graph forms a bell shape and a symmetric. Okay, and if you click on Fit Normal, right, you can see how well the normal curve fits the graph of the sample means. Okay, so you can remember that the mean of the sample means is equal to the population mean. Okay, and that's what we are observing. Okay, so the mean of the sample means is the same as the population mean of 16. And then the standard deviation of the sample means is given by this formula. So So sigma divided by the square root of n. So remember, sigma is the standard deviation of the population, and then n is the sample size. So if we take the standard deviation of the population and divide it by the square root of the sample size, we get the standard deviation of the sample means. Okay, so according to our simulation, the standard deviation of the sample means is 2.28. Okay, so if we apply the formula, which says that the standard deviation of the sample means is equal to the standard deviation of the population, 5.00. Alright, divided by the square root of our sample size. Okay, so our sample size is 5. The square root of 5 is this number here. So 5 divided by the square root of 5, right, should be equal to this number here. So in our simulation, it's equal to 2.28, and you can see that 2.28 is fairly close to the predicted value of the standard deviation of the sample means, which is about 2.23 or 2.24. Okay, so if we take more and more random samples, okay, so far we have over 70,000 random samples. Okay, the graph of the sample means is still normally distributed. The mean of the sample means is still 16, but now we see that the standard deviation of the sample means is much closer to the value that's predicted by our formula, which is about 2.23 or 2.24. Okay, so you can see that the central limit theorem works if the population is normally distributed and the sample size is small. Okay, so you can actually do this for a larger sample size as well. Okay, so remember we're modeling the sample mean. Okay, and we can increase the sample size to 20. Okay, so how does that affect the results? Okay. Okay, so for sample size of 20, this is our sample mean. Okay, so the quicker way to do this is to click on either 5, 10,000, or 100,000. So that'll take random samples of each size from the population. Okay, so we already saw how this looked for a sample size of 5. So let's see how this looks for a sample size of 20. Okay, let's do 10,000 samples. Okay, then 10,000 more. Alright, so we get close to like 50,000. Okay, so you can see that yes, for a small sample size of 5, right, the sample means are still normally distributed. Okay, but if we increase the sample size from like 5 to 20, right, the graph gets more narrow, but it's still normally distributed. Okay, if you're to click fit normal, okay, the graph of the normal distribution models the graph we see here. Okay, and the mean of the sample means is still equal to the population mean. Okay, but what about the standard deviation of the sample means? So once again, according to the formula, right, it's equal to the population standard deviation divided by the square root of the sample size. Okay, so for samples of size 20, right, we should expect that the standard deviation of the sample means is equal to the standard deviation of the population divided by the square root of the sample size, which is 20. Okay, so we're going to take our population standard deviation, which is 5.00, and divide it by the square root of 20. Okay, and let's see what that gives us. Okay, so again, according to our simulation, it's approximately equal to 1.13. Okay, and according to the formula, right, 5 divided by the square root of 20 is equal to approximately equal to 1.12. Okay, so you can see that the central limit theorem still works even when we increase the sample size for a population that's normally distributed. Alright, now let's see how the central limit theorem works, okay, if the population is not normally distributed. Okay, so this is the graph of the parent population, which is definitely not normally distributed. Okay. So we'll do it both for small sample size of n equal to 5, and then a larger sample size of n equal to 25. So you may remember that the central limit theorem applies if the population is not normally distributed, so for any population, right? But the sample size has to be at least 30. So unfortunately, with this this applet, right, the largest sample size we can select is 25. So that's the best we can do. Okay, but let's see how this works. Alright, so let's take a random sample from the parent population. Okay, for a small sample size and for the larger sample size of 25. Okay, so the mean of the small sample size, right, is here, and then for the larger sample size is here. So if we click animated, right, it shows you randomly selecting values from the population, okay, for each sample size that you select. So this is taking 25 randomly selected values from the parent population. Okay, and the sample mean ended up here. Okay, so let's do this again. Okay, and again. Okay, and one more time. So once again, if you click animated, right, it'll show you taking random values from your population, whatever sample size you have, and then it'll show you the resulting sample mean. Okay, so for the random sample of 25 values, the sample mean landed here. Okay, so obviously that's not the best way to see the shape and distribution of the sample means. So let's go ahead and click 5. Okay, so it'll randomly take 5 samples from our parent population and then compute the sample mean of each, and then graph the resulting sample means. Okay, and you can see how many samples you've got, okay, for each sample size. So we have 30 random samples for each sample size from our parent population. All right, so let's do this until we have 100 different samples. Okay, so you have 100 different samples for each sample size. Okay, so you can see that for the smaller sample size, the graph of the sample means is more spread out, but for the larger sample size, the graph of the sample means is less spread out. Okay. So what happens if we do 10,000 samples? Okay. So even for the small sample size, right, you can see that the graph of the sample means is roughly normally distributed. Okay, roughly bell-shaped or symmetric, but we shouldn't expect that. Okay. But for the larger sample size, the graph is more symmetrical and bell-shaped. Okay, so the normal distribution models the graph of the sample means fairly well for a larger sample size. Okay, better than it does this graph. So this graph has a little bit of skew to it, although it's hard to see. Okay, let's do 10,000 more samples. Okay, so again, even for a small sample size, right, the central limit theorem, it doesn't guarantee that the distribution of the sample mean is normally distributed, but you can see here that the graph of the sample means for the small sample size is fairly bell-shaped and symmetric, but for the larger sample size, it definitely is more bell-shaped and symmetric. Okay, so let's look at the mean and standard deviation of the sample means for the larger sample size. Okay, so we can see that the mean of the sample means for random samples of 25 people or individuals from the population, right? The mean of all those sample means is equal to the population mean. Okay, that's what we'd expect. Okay, so the standard deviation here is equal to 1.89. Okay, so according to the formula, right, the standard deviation of the sample means should be equal to the population standard deviation, which is 9.40, divided by the square root of the sample size. Okay, so let's type in 9.40. Alright, and divide it by the square root of 25. And the square root of 25 is 5. So 9.4 divided by 5 is about 1.88. Okay, so that's what you'd expect. Okay, so according to our simulation, right, the standard deviation of our sample means for random samples of 25 individuals is equal to 1.89. Okay, which very closely matches the answer we're getting from the formula, which is equal to the population standard deviation divided by the square root of the sample size. Okay, so see, this is how the central limit theorem works, and we can see that the central limit theorem is definitely true, especially for larger sample sizes. Thank you for watching.